right. Hello, everyone. Looks like you're back for more, huh? All right. Well, where are we at here? We ready to get into the second part of partial fractions? Get the 6.3 done? Feel excited?
Sure.
Ready to go? Okay.
Yeah.
All right. So we're at the end here. Okay. If we can get through these problems, like I told you, got kind of the light at the end of the tunnel here. We're going to be talking about integrating rational functions. That's our main goal here, is to integrate rational functions. So just remember that a rational function from college algebra is a polynomial divided by a polynomial. So anytime you have a polynomial, you divide it by another polynomial, that qualifies as a rational function. And we could go back and spend the rest of the class just talking about, you know, what rational functions look like and the way they behave and certain properties of them. They have, you know, some of them have vertical asymptotes, some of them have horizontal asymptotes, some of them have holes, blah, blah, blah. Our main goal is, can we find antiderivatives of these? And we actually do have a process for this. We have a set of steps. Now, if I actually go through these steps and read through these, this can be somewhat nauseating to actually talk about what partial fraction decomposition is, because of all the notation. It just looks horrible. I think it's better just to work through some specific examples to remind you how we do partial fractions. But let's get to the beginning of the steps. Okay, so the first thing you want to do when you're trying to integrate a rational function, well, the first thing you want to do is make sure you can't do it with something else we've already learned. But if you can't, then the first thing you want to do is inspect the degree of the numerator and denominator. So remember, the degree of a polynomial is the highest power of x that you see. So we want to look at the numerator, look at the denominator, look at the degrees, and then we have a couple of cases. If the degree of the numerator is less than the degree of the denominator, then we're just going to move on to doing the next step. If the degree of the numerator is greater than the degree of the denominator, then we're actually going to have to do long division to start the problem. All right, so case A is the easier case because that means you don't have to do long division. Case B, you have to do long division. So numerator less than denominator, we move on. If they're greater than or equal, then we must go long division first. And then we go into partial fraction decomposition, which again, I'm not going to go through all those steps. So let's just take this first example. Let's work through it and let's see what happens. All right. Here we go. So we're trying to integrate this. Now, can we do this with some other method, like a basic U sub or integration by parts or anything else? Probably not. I don't see anything obvious that we could do that would make this thing work. But it is a rational function. Do y'all agree? We have a polynomial on top. We have a polynomial on the bottom. The degree of the numerator is 3. Right? So the numerator has a degree of 3. And the denominator has a degree of what?
1.
1, because the highest power of x we have down there is 1. Right? So the degree is 1. So in this case, the degree of the numerator is bigger than the degree of the denominator. And so our first step is long division. Okay, that's the first thing we're going to do. So we must do, this implies that we must do long division first. Now, long division is something that you learned a long time ago, and we need to be able to do it, all right? So here's what we're going to do. Our good old division box. And inside that division box goes the numerator. Now I'm going to put x cubed. I'm going to put 0x squared plus 1x, or just x. So Notice that I put a 0x squared in there. That's a placeholder. That keeps everything in order so that you don't accidentally get variables overlapping one another. And then on the outside, you put the denominator, the polynomial, in descending order. Oh, by the way, both of these have to be in descending order. So highest power of x, and then you just work your way left to right. So now we just play this game. We look at the x out here and we ask ourselves, what do we have to multiply x by to get x cubed, right? So we say, okay, x times x squared, right? So we put x squared there. And some professors tell you, you need to put it like over the x squared here. It actually doesn't matter where it goes. It's just slap it up top somewhere. So I'm going to put it here. Okay, now, can someone tell me what the next step is?
We multiply the -1 with the x squared.
Yes, well, we have to do both. We have to actually take this x squared and multiply both of those by x minus 1. All right,
And then
so
subtract the whole equation. So x cubed negative x squared. And
yeah,
then we
negative x squared. Now
and then
notice,
we do the change of sign.
yeah, we'll change the signs, but notice that 0x squared, that's why we have it, so that we have a place to put the x squared underneath it. If we didn't have that 0x squared, like if we would have just done this, then when we did this multiplication, we got x cubed, we go here, but then when we get the negative x squared, it's like, where do we put it? Right? You can't put it under ax because you can't combine those together. So that's why we have to have that 0x squared there. Okay, so now what you do is you come through and you change the signs. Really what we're doing is subtracting this row. We're subtracting that bottom row, and to subtract it means to change the signs. So minus and then plus, right? And now we just add straight down. So the x cubes go away. I'll have an x squared here, and I must bring this x down also, plus x. And then once we do that, we play the game again, right? We play the game again. We go back to x cubed. I mean, sorry, to x, and we ask ourselves, what do we have to multiply x by this time to get x squared? So just x, right? So we put that up top. And then we do the same thing. We multiply here, we put it underneath, and we subtract. So x times x gives me x squared. X times -1 gives me negative x, right? Then we come through, do not forget to change the signs. I think I'm going to change the signs in a different color here. Minus this, plus that. And see those, the x squareds cancel, but the x's don't, right? They add together and they become 2x. And then we play this game again. We keep playing it until what we're trying to do doesn't work anymore. So I'm going to look at the x here. I'm going to try and turn my x into 2x. So I'm missing a 2, right? I just need to put a 2 here, so plus 2. And then I do it again. I multiply the 2 here and the 2 here. So I'll get 2x and then minus 2. I come through, I change the signs, I add down, the 2x's go away, and I just have a 2 here. Now, at this point, we would again play the game. We would say, what do we multiply x by to get 2? And that's where we have to stop, because you can't turn x into 2, because the 2 doesn't have any x's. So the 2 down there is our remainder. And so what we do is we put up here R2. No, that's grade school, right? That's what we do in elementary school, right? We put R2. That's not what we do in here. Here, what we do is we say plus the remainder over the divisor. It's always this number over that expression. Goes on the outside with a plus sign. Okay, does that ring a bell? Long division, does that ring a bell? Okay, so what does this mean? Well, I mean, it means exactly what division means. Look, if I say take 15 divided by 5, I'm sorry, 15 divided by 3, and you do 15 and you do 3 and you put a 5 here, what we're saying is that this is equal to 5, right? Whatever that answer is, that's what it's equal to. So we're saying the exact same thing here. We're saying that this integral that was initially all that is really just this. That's the same thing. So we can just rewrite x squared plus x plus 2 plus 2 over x minus 1. And what's great about this is now I've got a bunch of addition signs, right? And I can just do like power rule, power rule, power rule. And then this one is a constant over a linear, right? And that's what we talked about at the beginning of class last time. We said, hey, look, we're going to go through 8 examples of things that we should know how to handle. The first one we did was a constant over a linear, right? So I should be able to handle that. So I'm going to go straight to the answer. 1/3 x cubed plus 1/2 x squared plus 2x plus 2 natural log of x minus 1 plus c. And I don't have to scale that because there's a 1 in front of that x. I don't have to scale that natural log by anything, right? I still have to have the 2 that was here. That's out front. But the rest of it's just natural log of x minus 1. And that's it. We're done. We actually, with that problem, we were able to just do long division. And what we got, we could handle. We did not need to do partial fraction decomposition for this problem.
All right, so in that case, Professor, if it would have been x cube minus 1, we'll have to do the same, but we need to scale the natural log
Wait, if it would have been x cubed minus 1 where?
at the just on the last section of that integral. Instead of
that what
having x minus 1, yeah, if it would have been x cube minus 1, we could treat it the same, right?
No, because this is not a constant over a linear expression. This is a constant over a cubic function, right?
Mhm.
You can only do the natural log thing if what's on the bottom is linear.
If it's linear, okay.
Yeah, and this wouldn't be. So, you know, the question would be, how do you do that? Well, that's something we should be able to figure out today. But not right now. We can't do this yet.
Okay.
But let's keep that on the table because I can do that problem later. All right.
Mhm.
Okay. All right, let's look at the next one then. That wasn't so bad, was it? I mean, as long as you're okay with long division, that wasn't so bad. Okay, first step, make sure that this isn't something that you can handle, right? Is this something we can handle? Sure doesn't look like it, does it? It is a rational function. It is a rational function. You have a polynomial on the top, polynomial on the bottom. The degree of the numerator is 2. The degree of the denominator is 3. So in this case, the degree of the numerator is smaller than the degree of the denominator. We only use long division if the numerator is bigger than or equal to the denominator's degree, all right? If it's smaller, like it is in this case, we don't do long division, all right? We go now to the next step, which we haven't talked about, which is partial fractions.
I have a question here.
Yeah.
So in calculus, not in calculus, in pre-calc, I believe we did partial fractions.
I hope you did.
It was some type of, I don't remember exactly what it was, but I think it was the very first topic my teacher went on, and it
Yeah.
was about fractions.
Yep. Yeah, so I know that a lot of you aren't going to remember exactly how to do it. So I'm going to go through it. And hopefully as I go through it, things will start to like, oh yeah, I remember kind of doing that. All right.
So is it pretty much same as what we did in pre-calc?
Yeah, that's why you did it in pre-cal. You did it in pre-cal so that when you get to Cal 2, you can handle this.
Oh, okay. Thank you.
Yep. Yeah. So it's the exact same. We're going to do some algebra here. That's how we're going to start this problem out. So let's just take a quick poll. I'm just going to do a quick poll here. When I say partial fractions, do you feel good about it? Yes. Or do you feel not so good about it? No. Okay. All right, so I have about 56% of you, more than half of you feel pretty good with partial fractions and the other part don't. Okay, so I'm debating right now how deep I want to go into this. I'm going to just try and just skim the topic real quick, just to give us a feel for what the hell partial fractions is all about. So here's the idea. Let's say that I had, just forget integrals for a second. Just say I had this expression and I wanted you to add these two things together. Okay, what if I wanted you to add those together, just algebraically? You're adding two fractions, you have to have a common denominator, don't you? So you would have to multiply this one over here by x minus 3. You would have to multiply this one over here by the other denominator, x plus 4. And that's how you create common denominators, right? You're going to now have the same denominator here as you have over here. So when I multiply 1 through the top there, I get x minus 3 over that common denominator. And then I have plus, now I have to distribute the 3 through here. So I'm going to get 3x plus 12 over the common denominator, x minus 3 times x plus 4. Now I can put them together because they have the same denominator, right? So I can go x minus 3 plus 3x plus 12 over the common denominator. I can simplify the numerator to be 2x plus 9 over, and then the bottom I could actually FOIL that out. That's x squared. I should get plus x minus 12 when I put it all together. And this is what it would be. So if we started here with this in red, back in college algebra, and we were asked to put it together, right, into a single expression, you should get this. Yes? That's not partial fractions, okay? Going from the top to the bottom is not partial fractions. Partial fraction decomposition. Partial fraction decomposition is starting here and going up to here. Okay, that's what partial fractions is about. It's about starting with that expression on the bottom and trying to turn it into the one on top. Now, why is that useful to us? Well, if you're trying to integrate this, right? No, thank you. I'd rather integrate oh shit, I'm messing things up here. I'm still messing things up here. I'd rather integrate this. Why? Why would you rather integrate this than this?
Because there's a plus sign in there and you can
Plus sign.
integrate them separately.
Each of these is just a constant over a linear expression, right? I'd much rather deal with this than deal with this. So we need a process to go backwards, and that's what partial fractions is all about, going backwards. Now let's actually do a problem and talk about the process. Again, when you do this in pre-cal or whatever, whenever you saw this, you obviously spent more than one day on it. You probably spent at least a week on it, if not more, maybe 3 class periods on it. So there's no way that I can realistically cover everything here right now, but I think I can give you enough to get you going, all right? So we know that we have to do partial fractions. So the first part of this is to look at the expression and factor out the denominator. Don't worry about the numerator, just factor the denominator. So yes, you have to be able to factor. So I look at the bottom, I realize I have a GCF, right? A greatest common factor. I have something that appears in all of them, and that's a single factor of x. So I'm going to pull out that single factor of x. I'll be left with 2x squared plus 3x minus 2. And then I look at this part here that has the 3 terms, and I notice that that's a quadratic trinomial, right? 3 terms. And so I ask myself, does that factor? So I kind of come over here to the side and I ask myself, does 2x squared plus 3x minus 2 factor? So does it break down to be something here? And so this is where a lot of this is going to depend on like your comfort level with factoring, right? You're all Cal 2 students, so you should have some level of comfort with factoring trinomials. This one, I believe it does factor. Let me see here. I believe that's the factorization of it. You could check it, right? Just check it by foiling it. You get 2x squared, you get 4x, take away an x, that's 3x, and then -2. Yeah, that's it, okay? So look, this step from here to here, we're not spending time on, all right? You should have done that two classes ago. But if you need to go back and refresh, just put a star here and say, hey, I need to go back and look at factoring again. Because you can't be spending 15 minutes on the test trying to factor a trinomial. You've got to be pretty efficient with it. Okay, so now I have pulled the x out, and then I know that the rest of it is 2x minus 1, and then x plus 2. Okay, so here's where we are, right? We are doing partial fractions. The first step was to just try and factor out the denominator as best as possible. There's nothing else we can do in terms of factoring. So now the partial fraction decomposition begins, and I'm going to do it on the side. So the way partial fraction decomposition works is you take the expression, the whole thing. I'm not looking at the integral at all. I'm just looking at the expression here. And what you're trying to do is figure out how to go backwards to a bunch of things that are going to be added together. Kind of like I said with this one. Here we started with this ugly expression, and somehow it becomes these things that are added together. All right? Somehow it does. So what you do next is you look at your factors. Okay, look at each of your factors in the denominator and inspect them and discuss or mentally have a conversation with yourself about what they are. Okay, what type of factors they are. So let's take a look at this first factor, x. Does everyone agree that that's just a linear factor? X by itself is linear, right? Okay, then we look at the next factor, 2x minus 1. Again, another linear factor. Right?
Mhm.
And then we look at the last one, x plus 2. That's another linear factor. They're all linear. Not only are they all linear, they're all distinct. Distinct meaning that they are all different, right? They're not the same factors. Like if this would have been x, and then what if we had x plus 2 here in green and x plus 2 there again? Those two would not be distinct. Those would be what we call repeated linear factors. So we're not dealing with that yet. We will later. But for right now, we have, do you agree we have three distinct linear factors? Yes?
Mhm.
Okay. So if you have 3 distinct linear factors, that tells you something. That tells you that this thing should split up into 3 different things. It should be some fraction plus some other fraction plus some other fraction. You know that because you have 3 distinct linear factors. If you had 5 distinct linear factors, then you know it breaks up into 5 things. If you had 2, then it'd be 2, right? Pretty straightforward. The thing is, what does it break up into? Well, the good news is that you know the first fraction will have the first linear factor on the bottom. The second fraction will have the second linear factor, and the third factor will have, or the third fraction will have the third distinct linear factor. The only thing you don't know, right? The only thing you're unsure of at this point is what's on top. And anytime you have a distinct linear factor, we know that these fractions over here, these tops, these numerators are all going to be numbers. They're all going to be constants, but we just don't know what they are. So we're just going to call them A, capital B, and capital C. Now, our goal at this point, our goal is to find A, B, and C. Now think about why that's going to be nice. if I could somehow determine that A was, let's say, 1 and B was 2 and C was 5, then wouldn't you like to integrate each of those? Wouldn't it be nice to integrate those? Because each of those would be a constant over a linear factor, constant over a linear factor, constant over a linear factor. All those would turn into natural logs when you integrate. Life is great, we move on, right? But we have to find the A, B, and C. So how do we do that? What we do is, I guess I can do it. I'm going to kind of rewrite it down here. Can somebody tell me what I'm about to do? Take this original thing.
We're supposed to
rewrite everything.
find, what is it, common denominators for each letter?
Okay, yeah, it's something like that. I'm gonna do something like a common denominator, not quite. I'm not gonna combine these things on the right-hand side together. I'm not trying to put them together. What I'm gonna do is I'm gonna try and clear the fractions out completely. I wanna get rid of the fractions. So what I'm gonna do is I'm gonna recognize that the common denominator that we have, that we could have, would be this. And we could just multiply both sides of the equation by that common denominator. So I'm going to multiply the entire left-hand side by this. And I have to multiply the entire right-hand side by that. Now, the reason I'm doing that is because on the left-hand side, everything here goes away. Everything. Except the numerator. The numerator is still there. Do you all agree? Now on the right-hand side, you have to be careful, all right? Because when I distribute this, when I do this first multiplication from here to here, all that stuff in black goes on the top, right? With the A. And then I still have an X on the bottom. So that X that came through with the black is going to go away with the X on the bottom. But I'm still going to have the A there. I'm still going to have the 2x minus 1 there. And I'm still going to have the x plus 2 there. Is that clear to everyone? That the x is canceled when I distributed that through. Similarly, when I multiply this through to here, I'm going to have the b. Will I have the x? Will I have that x still?
Yes.
Yes. Will I have the 2x minus 1?
No.
No, it's going to cancel with the 1 on the bottom. Will I have the x plus 2?
Ah, okay.
Yes, I will. Do y'all see?
Now we do.
Yes, okay. Plus, now I did the last one. I have the c is going to be there. Now, does the x cancel?
No.
No. Does the 2x minus 1 cancel?
No.
No. How about the x plus 2?
Yes.
Yes. Okay. So this is my new equation. So when you look at this, you should just kind of take a step back and think about this. We have a single equation, don't we? We have a single equation, and we have 4 unknown variables here. We don't know what A is. We don't know what B is. We don't know what C is. And we don't know what X is, right? There's 4 things we don't know. So what we're going to do now is we're going to try and figure out somehow from this what A, B, and C are. So in doing this, there are 2 methods on getting A, B, and C. There's what I like to call the short method, and then there's the long method. Now, the good news about the short method is it's short, okay? It goes fast. The bad news about the short method is that it doesn't always work. Like there are some problems where you can't use the short method. The long method sucks because it's long, but the good news is that it always works. So I'm going to do both. So I'm going to do the short method first. Okay, the short method is us. What we're going to do is we're going to be clever, super clever. All right, we're going to be very, very clever. We're going to look at this equation we have, and we are going to ask ourselves, well, we're going to say to ourselves, let's go find A. Okay, let's go try and figure out what A is. And what we're going to do is we are going to let X B something. So we're just going to assign a value to X, but not just arbitrarily assign it. We're going to be clever about it. So if I'm trying to find A, I would really like it if B and C weren't around, if they could somehow vanish from the problem, right? If B and C could be gone, then maybe I can find A. So I'm going to look at this, and I'm going to look at this, and I'm going to ask myself, what value of X could I plug in to both of those that would kill those things off completely?
0.
0, right? If X was 0, both of those terms would go away. Yeah. So I'm just going to let X be 0. And now what I'm going to do is I'm going to rewrite everything in green, everything that I see in green. I'm going to rewrite it, replacing X with 0. So what does the left-hand side of the equation become?
-1.
-1 equals, okay, I have A. And then what about that first parentheses? What happens in here when I replace that X with 0? What do I get here?
-1
-1.
and 2.
And then when I replace that X with 0, I still have +2. So that's going to give me 2. And then plus, what can you tell me about this piece here? When I replace that X with 0,
0.
0, and it kills everything here, right? That's why we chose it. So I'm going to have nothing there. And then the last piece, I let X be 0 there. So it killed everything off there. And check this out. What do we have? We can put the -1, the 2 together. It gives me -2 times A. So -2A equals -1/2. Solve for A. A is 1/2. So now I know what A is, right? I know what A is. All right, that worked. And it wasn't too bad. I just had to think about what X needed to be. So now what I'm going to do is I'm going to say, okay, let's use that same logic and let's start over. Let's go try and get B. So if we go and try and get B, I need to let X be something. Okay, so I want to preserve this term. So I want to kill the A term off and the C term off. What am I going to have to choose for X? It's not as obvious this time.
-2.
1/2 positive.
So what they both have in common is this factor and this factor, right? That's what they both have in common. You need to pick an X that's going to make that factor a 0, right? I heard someone say that was correct, 1/2. But the way you're getting that is just take that factor and just ask yourself when it's 0, right? So just solve that little equation. 2X equals 1, X is 1/2. And so that's what X has to be, 1/2. So if I let X be 1/2, then it should have the effect of killing this one off and this one off, and all we'll be left with is that middle one. Make sense?
Mm-hmm.
Okay. So now unfortunately, that 1/2 has to go to everything. Okay, it can't just be on the right side. It's got to be on the left side too. So you got to put a 1/2 here, a 1/2 here, 1/2 here, 1/2 here, everywhere. So I'm going to do 1/2 squared. That's 1/4. Plus, let's see, 2 times a 1/2 is 1. Minus 1, that's the left side, equals. Now, what can you tell me about this whole piece here with A? What can you tell me
It's
about
gonna
that?
be 0.
0.
It'd be 0, right? That's what, by design, that's 0. Okay, plus now the B one's going to still be there. We're going to have B times X, which is a 1/2. And then we have to do what here? That was a B times a 1/2. Now we have to do a 1/2 plus 2. 1/2 plus 2 is 5/2, right? I'm just going to keep it as a fraction. I'm not going to go to decimals. That's 5/2. And then that last piece should go to 0 also. Any questions? It's fun? All right, the left side of the equation becomes 1/4 equals, okay, I need to put those together. These two numbers put together, multiply, I'm going to get 5/4. And then I still have the B. And then I'm going to multiply both sides by the reciprocal. So I multiply both sides by 4/5. And that will give me 1/5 equals B. All right. We are 2/3 of the way there. We have A, we have B. Let's go get C. So for C, I'm gonna just have to do it over here. I need to let X be something here. Not 0, sorry. So
You can let it be 1 and put all the values of A, B, and then find C.
I'm sorry, say again.
You can let X be a 1 and equate the values for A and B and then just solve for C.
Yeah, you could let X be any number you want at this point. Replace A with a half and B with a fifth and go solve for C. I agree, you could do that. But
Isn't it that dangerous? Like if you get the wrong number, then everything's gonna be wrong.
well, not really, because, and the only reason is because remember, we have 4 things we don't know, right? Well, we started with 4 things we don't know. Now we know A and now we know B, right? So if you just let X be any number now, then the only thing left is C, and so we can solve for it. We can't do that in the beginning. In the beginning, we have to pick very special numbers.
Mhm.
But I'm gonna stick to the same method we've been using here. I'm gonna try and kill off.
Because if we do something, say, call it B in fraction, if we multiply that wrong, then we
Yeah.
got a wrong value and then we're screwed, right?
Yeah, I don't
With
want to
the
mess
rest
with
of,
fractions. Yeah, exactly. I don't want to mess with the fractions. I'm gonna try and kill those blue pieces off. So I'm gonna need to let X be -2. Does everyone agree? That's what, those both have this X plus 2 factor in them. And so if I let X be -2, it's gonna make those factors 0. So I'm gonna let X be -2, and then I get to rewrite everything again. So yeah, and this is the short method. Plus, actually, is that gonna be plus? What's it gonna be?
minus, no?
-4, and then -1 equals, okay, I know that the first part goes away. I know that the second part goes away. So I have nothing there, I have nothing there, and then here I have C. I'm plugging in -2 for X, and then I get a -5 there. So just be careful, you're plugging in -2 here, -2 there. So this becomes -1 equals 10C. Divide by 10. C is 1/10. Oh, what?
No.
Okay. Any questions? Okay. If there are no more questions, let's go get the answer. I'll do the long method after we get the answer. So here's what we're gonna do now. We're gonna go back to the original integral. But instead of putting all this crap in here, right, we're gonna replace it with this. But we know what A, B, and C are, don't
So
we?
I have a question.
Yep.
So I remember in pre-calc, once we get these let X be, when we find the values of A, B, and C, we just equate the values on top of each denominator, and that's the part we're done. But
Yeah,
here,
that's right.
since it's calc 2, we're gonna integrate it now.
That's right. Yep.
Okay.
Yep.
So how much was C? 1/10?
-1/10? -1/10,
Oh, yeah.
right? Because this became a -1 over here.
Yeah, minus and minus is plus. I
Yeah,
got that
that's
wrong.
right, there it is, a plus. Okay, so A was a half, B was a fifth, and C was -1/10. So watch the way I write this. And I think when I write it, you'll appreciate why I'm doing it this way. All right, first thing I'm gonna write is what you see here in that purplish color, A over X. But instead of writing 1/2 over X, I'm gonna write it this way, 1/2 times 1 over X. So really what I did is I just pulled the 1/2 out front. I'm gonna do the same thing on the next one. B was what, 1/5? So I'm gonna do 1/5 times 1 over 2x minus 1. And then the last one was, C was -1/10, so I'm gonna pull the -1/10 out as a constant, and then I have 1 over x plus 2. dx. And now I have 3 integrals that I can handle. All of them, right? All 3 of these pieces are constants over linears with some constants out front that I can just bring along for the ride. So my answer should be, All right, the 1/2 comes down. The antiderivative of 1 over x is just natural log of the absolute value of x. Plus the 1/5 comes down, comes with me. And then be careful here. We need to take the antiderivative of that part, 1 over 2x minus 1. So I've already put the 1/5 out there for you. What do you need here? What's going to be?
2 natural log of,
Close, not 2. You're trying to get rid of the 2.
1/2.
1/2. You have to scale by 1 over 2. Remember, you're scaling by 1 over a. So because we have a little 2 in front of that x, I have to scale by 1 over 2. And then comes my natural log of 2x minus 1. Is that all right? Then the last one, minus 1/10. And then for this one, I don't have to scale because I have a 1 in front of x. So this is just going to be natural log of x plus 2. Plus c. Life is good. I can put those two together, but I'll just leave it there. All right, there you go. That only took us 30 minutes or so.
Wow.
hopefully in the exam would take us 5, 7.
5 to 7 class periods.
No, 5 or 7 minutes
Oh,
during
okay.
the exam.
Okay. All right. So that's the short method. All right. And like I said, the short method doesn't always work. For this problem, it does. Let me explain why it works here. The reason it works is because when we were trying to get A, there was an X that we could choose that would kill off B and C. When we were trying to get B, there was an X that we could choose that would kill off A and C, these pieces. When we were trying to get C, there was an X we could choose that would kill off these two. Later on, we'll see a problem where you can't do that. All right, there's going to be something where you just can't kill off the other two. Like the other two that are sitting there can't be killed off.
Oh,
Yes.
so I remember at that part, we do the substitution or the elimination method by keeping them 2 equals to each other.
Yeah, we're going to do that. So I'm going to take this. I need to do this on a different page. So we're done with the problem, but now we're going to do this, just this portion of the problem again, trying to find A, B, and C. We're going to do it with the long method. Okay, long method. So what you do for the long method is you multiply everything out. Get rid of all your parentheses. So the left-hand side is going to be x squared plus 2x minus 1. Nothing changes there. Equals, okay, so if I multiply these two together, don't worry about the A. If I multiply that together, I get 2x squared. I get plus 4x minus, so that's going to be plus 3x minus 2. If I multiply those two together, I'm going to get x squared plus 2x. And if I multiply those two together, I'm going to get 2x squared minus x. Do y'all agree with that? That's what you would get if you multiply those together?
Mm-hmm.
Okay, now remember this part here that I did first, I had an A in front of all that. So basically every single one of these terms is going to get an A attached to it. So it's going to become 2a x squared plus 3ax minus 2a. That is just this right here. Okay, now let me do this piece. So it's going to be the x squared plus 2x, but everything gets a b. So we get plus bx squared plus 2bx, and that takes care of the middle piece. Then I do last piece, so every one of those gets a c, so 2cx squared minus c times x. That's the last one. All right. So we got rid of the parentheses. Now what we're going to do is collect like terms. So like terms means we have to have the same variable raised to the same power. So in other words, I'm going to be collecting, let's get all our x squareds together. I have an x squared term there, I have an x squared term there, I have an x squared term there. I'm going to put all those together up front. 2a x squared plus b x squared plus 2c x squared. Okay, that's everything in yellow. Now let's get our x terms. We have a plus 3ax. We have a plus 2bx. Let's put those together. Oh no, we have a plus, I didn't see that one back here, minus cx. Almost forgot that one. That would have been bad. So we have plus 3ax plus 2bx minus cx. So now I've got the blue piece together. And the only thing left that I haven't dealt with is the minus 2a, which is the only piece that doesn't have an x on it, right? Okay, next step. Is from these, I'm going to group these. This was our yellow, this was our blue. I didn't give the other one a color here, green, right? Okay, so all the yellows have an x squared, don't they? All the yellow ones have an x. I'm going to factor out an x squared. I'm going to pull an x squared out of all three of those terms. But watch the way I do it. I'm going to put the x squared behind it. So normally when we factor things out, we put it out front, right? But there's nothing wrong with putting it in the back because it would still distribute through. I'm going to do the same thing over here. I'm going to pull the x out of all of these. And we have x. Then the only thing left is minus 2a. All right, we're getting close. Any questions on that step?
No.
So now what we're going to do is we're going to realize that in order for this to be a true equation, right? In order for that to be a true equal sign, it's like a scale. The left-hand side has to be equal to the right-hand side, right? And what we realize is that on the left-hand side, don't we have just one x squared there? Right?
Mhm.
And on the right-hand side, don't we have this many x squareds? We don't know what that is, but that's how many we have. So for this equation to balance, I need this and this to be equal to one another. In other words, I need 2a plus b plus 2c. That must match up with the coefficient on the other side of x squared, which is 1. So I'm setting this coefficient equal to that coefficient. And I'm going to do that for the rest of the equation. I know that the coefficient in front of x, all of this, must match up with the coefficient in front of x here, which is 2. So I have 3a plus 2b minus c must equal 2. And then the last thing by itself that does not have an x on it must match up with whatever over here doesn't have an x on it, which is this, -1, which means that -2a has to equal -1. And what are we looking at here? What is this over here now that we have?
A equals 1/2.
System of
Okay.
equations?
Yeah, we could solve for A. We have a system of equations. We have back in college algebra what we refer to as a system of equations. In fact, these are linear equations. That doesn't make a difference. System of linear equations. And this is actually a system of 3 equations and 3 unknowns, right? We have 3 equations and we have 3 things we don't know. So how do you solve systems of equations? Do you remember from college algebra how we solve these?
There was the substitution method.
There's substitution. And then the other
Isn't there
one,
elimination?
elimination. Those are the 2. Now substitution is really good when you have 2 equations and 2 unknowns. But once you get to 3 equations and 3 unknowns, elimination's better. Now, we're all Cal 2 students, so at some point we've done this. So I am going to not require that you do this by hand. I'm going to encourage you to do it, or I'm going to want you to do it using your calculator. So we need to take a poll. How many of you have a Texas Instrument calculator, graphing calculator? How many of you do not? Or have access to a Texas Instrument calculator? You may not have one right now, but you can get one. No, I'm not saying buy one. You know someone who has one?
That doesn't mean that we know how to use it, correct?
No, that's right. You don't know how to use it. Okay, so we have 3 people who don't. So the 3 people who don't, do you have something else? Do you have a different graphing calculator or just don't have one?
I have the Casio one, this one. I don't think.
Yeah, that's not gonna work. Well, you know what? That Casio might. Let me see it again. You know what? That might do a system of 3 equations, 3 unknowns. I'd have to look. So what I'm gonna do right now, I'm not telling you you have to go get a Texas Instruments calculator, but I would start scrounging around for one. If you can find a friend who has one or something, you know, to try and get one. Because I'm gonna show everyone how to solve the system of equations with the Texas Instruments graphing calculator, all right? Now, let me say a couple of things here before I start showing you how to do this. Number 1, there are shorter ways to do this on the calculator. Like if you're really good with your graphing calculator, you may know how to enter a matrix and do all this stuff. What I'm gonna show you works on all of those calculators. So I'm trying to show you like the keystrokes that's gonna work for all of you, like for every calculator, whether or not be the TI-84, TI-83, TI-86, TI-89, doesn't matter which one you have. This should work on all of them, all right? So here it is. Maybe, hold on, I gotta bring up my thing. Oh, there it is. Okay. Okay, can everyone see that okay?
Mhm.
Okay, so first things first. This thing's not where I need it to be. It's weird, every time I move it, it gets real, wants to go back here. Okay, that's all right. All right, so over here, where we're working, right? Where we're working, I want us to all rewrite this in what's called its matrix form, which means all we do is we write the coefficients of the numbers, 2, 1, 2, 1, and then we have 3, 2, -1, 2. Then we have -2, 0, 0, -1. Okay, this is called an augmented matrix. And don't worry about that. Like, you know, what's major? We're not getting into that. I'm just telling you that's what it's called. It's just all those equations rewritten where you just look at the numbers in front of the variables A, B, and C instead of, we don't have to keep track of the letters. All right, so what we're gonna do, we're gonna somehow put that information into the calculator. The calculator is gonna go through and do something. It's gonna do elimination for us. And then it's going to spit out an answer that looks like this: 1, 0, 0, and then it's going to give us a number. And it's going to give us 0, 1, 0, and then a number. And it's going to give us 0, 0, 1, and then a number. Now, if you look at that and you go back and you replace the A, B, and C backwards, like go from the numbers back to the equations with the A, B, and C in it, that first equation is A equals a number, because notice there's zeros here for the B and the C. The second equation is what?
B.
B equals a number. And then the last equation is C equals a number. And so essentially the numbers down the side here represent your answers for A, B, and C. Now the operation that we're going to use, we're going to have to pull up an operation on our calculator to do this for us. The operation is called RREF. That's the name of the function that's built into the TI calculator, RREF. It stands for reduced row echelon form. That, if you take linear algebra, you'll hear about that more, but that's what we're doing. We're taking a matrix and turning it into its reduced row echelon form. Basically, we're getting diagonal. The diagonal is going to have 1s in it and everything else is 0. And that's reduced row echelon form. All right, you ready to do it? We're going to do it on the calculator.
Aren't those like matrices,
Yeah.
right?
Yep.
I
Okay,
have
so
the
I don't know
option
why I
on
have
here.
isn't there a method called Euler method?
a what?
A Euler, it's a mathematician to get the values of A, B, and C. I don't know the process.
Euler's method.
Euler's, yeah.
People say that his name different ways. They say it Euler, they say it Euler. I mean,
Euler.
there's a big debate about it, but anyway.
We got calculators now. That's what matters.
Yeah, well, no, I mean, we're using Gaussian elimination is what we're using. We're using, now Gauss was a different mathematician. So when you do elimination, you're actually using the method of Gauss. Does Euler have a method for solving systems of equations? Probably, but we're using the computer, which is based on a program written to use elimination. It's going through the algorithm using elimination. All right, y'all ready? Here are the keystrokes. Clear this out first. First thing I'm going to do is I'm going to try and bring up my matrix menu. So for me, the matrix menu is right here in blue. Some calculators actually have a matrix key. So I'm going to go matrix. And then what I'm going to do is I'm going to select math. So to do that, I have to hit the right arrow. And then I'm going to scroll down until I see RREF. Be careful, not REF, RREF. And once I do that, I'm going to hit the enter. That's too small. After that, I'm going to hit the enter key. Okay, so here's what our calculator has. It has sitting on the screen RR. I'm going to need more room. RREF parenthesis. All right, so that's where we are. So now what I do is this. I'm going to put a bracket in, not a parenthesis, a bracket. And the bracket is above the parenthesis, so I have to hit my blue key, bracket. Oh, no, hold on. I hit the wrong thing. Sorry. It's above the multiplication key. Not a brace, a bracket. Okay, so here's what we're telling the computer. We're saying, okay, we're going to do reduced row echelon form. Parenthesis meant here we come. We're going to start the function. The first bracket is saying I'm starting the matrix. Okay, so that first bracket says here comes the matrix. And then I do another bracket which tells the computer here comes the first row of numbers. And now what I'm going to do is I'm going to put this first row in here. Now the row I'm going to put in is 2, 1, 2, 1, first row across. So I'm going to put in 2, comma, 1, comma, comma's above the 7, 2, comma, 1, and that's the first row. So now I need to tell the computer I'm done with the first row. So I close that bracket, which is above the minus sign. There's my first row. Now I need to tell the computer I'm giving it a second row. So I do an open bracket again, and now I do the numbers across the second row. 3, comma, 2, comma, -1, make sure you use the negative key, not the minus key, -1, comma, 2. I need to tell the computer to close that row off
3, 2.
and start a new row. And this will be my last row, which is -2, comma, 0, comma, 0, comma, -1. What do you think comes next?
Two brackets.
2 brackets that closes the row. Then I close the matrix, and there's one more thing.
Close parentheses.
Close parenthesis, that closes the function. And now I hit enter. And there they are. There are your answers. That's A, B, and C. So let's talk about what those answers are. It's telling me that A is 0.5, which we all know is a half. B is 0.2, which is the same as 2/10, which is the same as 1/5. It's telling me C is -0.1, which is same as -1/10, which is -1/10, right? Same 3 answers. Boy, that was long, wasn't it? On a problem like this, I would never use the long method. I would always have done the short method. But I thought it would be a good exercise for us to just see how it works. Does anyone have a question on the input into the calculator or anything else?
I have a question.
Yes,
You always want our answers to be in fractions, correct?
I
For
think
A,
it's
B, and C.
better. I think it's better to have them in, it's not more right or wrong. You could put the decimal.
Okay,
I wouldn't take off. So if you wound up using RREF on your calculator and you got decimals and you put those in there, that's fine.
okay, thank
Yeah.
you.
Some calculators will give you the fractional answers. And I think there is actually a way to convert this.
Yeah, you go to math and then there should be a,
Math, and then I go here, this first one right there. So I just hit enter and it should take all the answers we just had to fractions. There we go, 1/2, 1/5, -1/10.
question.
Yep.
Can you click on your matrix button again?
Yep.
All right. So you can do what you just did, but with like the edit, you can edit those names. And
Yeah, are you saying I could go here and like go ahead and set up the matrix first?
yeah, and you can make it as big as you want and it does the same thing.
Yeah, so remember what I said. I'm doing it this way because the RREF function is built into all TI ROMs, okay? So all the TI ROMs have RREF in them. But the interface to get here to this matrix, like what you're suggesting, that interface is different for each calculator. So I'm trying to give you all keystrokes that will work for all of you. You bring up RREF and then it's the bracket thing, right? I mean, once you get good with the bracket thing, you can just put your own matrix in there. You don't have to go predefine it as like a 5x5 or something. You don't have to go through that step. You just use your brackets appropriately and you're in business. Okay, all right, let's move on. We need to do another problem. Whew. All right, where are we? Two down. Let's do this one. All right, we have a rational function. The degree of the numerator is 4. The degree of the denominator is 3. Long division, right? We've got to start with long division because the degree of the numerator is bigger than the denominator. So I'm going to do long division over here. X to the 4th plus 0x cubed, because I don't have an x cubed, minus 2x squared plus 4x plus 1. On the outside, x cubed minus x squared minus x plus 1. All right, so we play our game, right? We say, what do we multiply x cubed by to get x to the 4th? Well, we need an x. So I put an x here. Then I distribute the x through to everything. I'm gonna go a little faster on this, okay? Minus x cubed minus x squared plus x come through minus plus plus minus. And then I add down. What happens if you mess up your long division?
Unfortunate events.
It's over. At that point, everything else is going to be wrong, right? And I can't even imagine like the nightmare you might have when you try and do the problem later because things aren't going to be right. It's just going to be a mess. Take whatever extra time you need to make sure you get this step right. Okay, now, can we keep going with long division? Can we turn x
No.
into x cubed?
Oh, one.
1. Okay, so we can multiply by 1. And that gives me an x cubed here, minus x squared, minus x plus 1. I'm just multiplying everything by 1, so that's real nice. Everything just comes down. Now I change the signs, and I add down. Ooh, the x squareds went away too. Nice. Ooh, do I just have 4x? Yeah, okay. Now we stop because we can't turn x cubed into 4x. So that's my remainder. So I put my remainder over my divisor, which was that big ugly thing. So here's where we are. This original integral really turns into x plus 1 plus 4x over x cubed minus x squared minus x plus 1, all of that dx. And so here I'm partially happy because the first two terms now I can integrate, right? 1/2 x squared and then just x. So I can get that first piece. This third piece here, this piece, I'm still kind of like, not sure, right? But now we proceed. If you can't do that using any method we have, right? That's not natural log. It's almost remember last class we learned how to do a linear over an irreducible quadratic. We did that last time. This is not that case, but man, if that was x squared, just x squared on the bottom, I might be thinking that instead. But this is a linear over a cubic, and we haven't done this before. So that means we have to do partial fraction decomposition. So what I'm going to do now is this. I'm going to write down what the answer is up to this point. It's 1/2 x squared plus x plus this integral that I still haven't figured out. So the first thing we did on the previous problem, right? The first thing we did when I said we're gonna have to do partial fractions, I said to factor the denominator, right? Factor the denominator. So I think this would be a good point right now for me to just act like this is my new universe. Like my entire world now is revolving around that integral right there. Let's factor the denominator. Oh shit, how do you factor that?
Factor by grouping.
Factor by grouping, that's right, because you have 4 terms. So however it is that you learn to factor by grouping, I don't know. I mean, everyone's got their own way, the way they've learned. I always tell my students, you split it right after the second term. You split it, and then you try and find a GCF on the first 2 terms. So I'd pull an x squared out of the first 2 terms. You know what, I think I'm gonna factor it here and put the answer there. So I factor an x squared out of the bottom. Out of the first 2 terms, I'm left with x minus 1. And then you look at the second 2 terms, and you need to be able to factor something out that makes it match what we have on the left. So we need to have an x minus 1 over here. So I'm going to factor -1 out on the right, and that will leave me with an x minus 1. So that is this piece. And now since these 2 things match, this becomes just the part that matches times the 2 things that were out front. And does somebody recognize that we're not done factoring?
Yeah, you have the difference of squares.
Yeah, you have the difference of squares. So we have x squared minus 1 is actually x plus 1 times x minus 1. So I'm ready to put this new denominator over here. Watch what I do. I'm going to do x plus 1 times, I'm not going to write x minus 1 times x minus 1. I'm going to write x minus 1 squared. I just put those 2 together as one factor squared. All right, you with me? We have factored the bottom. Let's take some time to look at these factors and discuss them. We have here a linear factor, right? Okay, here we have what?
Quadratic.
Linear, but it's what? It's repeated.
Mhm.
Here it's repeated twice, right? So this again is now going to draw back onto your pre-cal or whatever when you did partial fractions. How do we deal with this? So I'm going to have to kind of start a new part here where I do my partial fractions. I'm going to put the part that we're trying to integrate here. Okay, so here's what I know. From the first linear factor, right? It's distinct from the other linear factor. They're not the same, right? So since that's a distinct linear factor, I know for sure I have x plus 1 on the bottom and some number on top. I don't know the number, but it's something. Now, does anyone remember how to deal with a linear factor that's repeated?
Don't you put
It was-
letter B over
B
x
over-
minus 1?
You got an X. to the end,
Bx plus C?
BX.
Hold on, CJ, were you talking? I don't know who was talking. CJ?
Yeah, and then you just put
Okay.
C over x minus 1 squared.
Excellent. That's it right there. That's it. So the way, here's what's happening. When you have a repeated linear factor, in this case, we have a squared. What you're going to do is you're going to put a constant over that linear factor. Then you're going to go a constant over that linear factor squared. Let's say that that power had been, instead of 2, let's say it had been a 5. Let's say it was x minus 1 to the 5th. Then I still would have done this. I would have done b over x minus 1, c over x minus 1 squared, but then I would have had to have done d over x minus 1 cubed plus e over x minus 1 to the 4th plus f over x minus 1 to the 5th. And I stop, I terminate when I get to the highest power. Yes? That's not what we have, thank goodness, right? But that's the method, that's the procedure. If you have a repeated linear factor, you just keep putting a constant on top of the linear factor and you keep increasing the power on that linear factor until you exhaust all the powers that you have.
Would
Now-
you give us something like that on the exam?
No, I wouldn't give anything like that. I'm just trying to get you to understand the procedure. So I'm going to erase all of this. If you look at the notes for this section, I am actually saying that somewhere here. Here it is. What if your denominator has some repeated linear factor? In other words, you have a polynomial on top, you have a linear expression on the bottom raised to the k. Then we must be able to find constants, a1, a2, a3. So instead of using a, b, c, I'm using these a with subscripts. And then I'm putting, look, the linear factor, then the linear factor squared, then cubed, then to the 4th, to the 5th, to the 5th, and you stop at k power. That's the way what I'm saying to you right now. That's the way it looks in like pure mathematical language. I think it's easier to speak than it is to write and understand. Do you agree?
Yep.
Yeah. Okay. All right. So there we are. So now we get to do what we did last time. We've looked at this linear factor. We've got it there, the a. We've got this piece squared. We've got that part right there. Now we clear the fractions. So we multiply both sides by the denominator over here on the left side. So I'm going to multiply both sides by that. This will always get rid of the fractions. That's why we do it. On the left side, all we have is 4x. On the right side, we've got to go here, here, and here. So let's do the first multiplication. We're going to have a there still. Are we going to have an x plus 1?
No.
No, it's going to cancel with the x plus 1 on the bottom, but we still will have an x minus 1 squared, won't we? That's still there. How about the second multiplication? We'll have a b, but let's see. I have an x minus 1 down here. Isn't that going to kill off one of these x minus 1s? One of them, not both of them though, just one of them. So I'm going to have the x plus 1. That never canceled. And then I still have an x minus 1. And then finally, when I do my last multiplication, I have an x minus 1 squared on the bottom, and that will cancel with the x minus 1 squared, and that'll give you your c, and then you'll still have the x plus 1. You good? Let's try the short method. Let's try the short method. Let's try and get A. How can we get A? Can we let X be something to get A?
Yes, we
One
can -1.
-1, because this piece here has a X plus 1, this one has X plus 1. So if I let X be -1, I'm in business, yes? Now, I'm not gonna go through that work. I'm just gonna pause that, and I'm gonna ask myself now, could I get B? So this is what we would get to do to get A. Could we get B? So how can you keep this, but get rid of both of these?
+1.
So +1 will get rid of this. Do y'all agree?
Yes.
Yes. But will +1 get rid of that?
Oh,
It
no.
won't, right? So you're not going to be able to get B. Could we get C? So could you get this? Well, you have to kill
Positive,
B
yeah.
off.
One.
Yeah,
X would
+1.
be 1. All right, so I should be able to get A, I should be able to get C, but I won't be able to get B directly, right? So what I'm gonna do is I'm gonna go with the long method. Now, you could do the short and try and work that, but I'm just gonna go long. But I'm actually gonna work a little faster because, well, we don't have time. So what I've done here is I foiled that out. That became X squared minus 2X plus 1. Hold on, what the hell did I do? Why did I put a 2 there? I messed that up. This right here became X squared minus 2X plus 1, and then I distributed my A through that, but I accidentally messed this up. This should have been plus A. And then I foiled that out, which came to be X squared minus 1, and then I distributed a B through that. It became this. And then here I just passed the C through this. I'm going to collect my X squareds together. And I'm going to pull the X squared out of them. So I got this one and this one, put them together, and then I pulled the X squared out. Now I'm going to put the X terms together, which is this one, and I'm going to pull the X out. And then everything that doesn't have X, I'm going to slap it to the end. Okay. On the left-hand side of the equation, I want everyone to understand that this really means, I'll do it this way, 0x squared plus 4x plus 0. Do you all agree? I have nothing in front of x squared. I have a 4 in front of x, and I have a 0 by itself. And the reason I'm doing that is because now what I'm going to do is match the coefficients. I know that a plus b has to be 0. I know that negative 2a plus c has to be 4. And I know that a minus b plus c has to be 0. 0. I'm going to write that down. A plus b has to be equal to 0. The other one, the next one says negative 2a plus c has to be equal to 4. And the last one says a minus b plus c has to be equal to 0. This is my system of equations, which I'm going to convert into a matrix. I know I'm working fast, okay? I know we're recording all this. You can go back and look at it, watch it, have a drink.
So I
enjoy.
figured out my Casio does matrices, but it's only 3 by 3.
Okay, that should be okay.
But this matrix is like 4
Oh,
by
yeah, because it's augmented. Well, I would have to look at the Casio a little bit more in detail.
So is there
Alright.
any way I could do it by hand then?
Have fun, yeah, if you want. Yeah, I mean, you could, yes. I mean, this could be solved by hand. You could, I would go back here and try and solve it. Like you could solve this first equation for A, take
Yeah.
that, plug it in here, and then try and get that. And then, yeah, I mean, there's ways, but we'll figure out a way for you to be able to use technology to help you through this, all right?
Okay.
All right, so now I'm gonna go to my calculator and do that. Matrix. Come on, man. Matrix. Math. Oops. Keep thinking it's a point and click here. RREF. And bracket, start the matrix, bracket, first row. What is it? 1, 1, 0, 0. Close it, open it. -2, 0, 1, 4. Close it, open it, 1, -1, 1, 0. Close it, close parenthesis, enter. -1, 1, 2. -1, 1, 2. Okay. -1, 1, 2. I've got kind of a cluster here. What I'm gonna do, I'm trying to figure out what I want to grab and take to the next page. I guess I'll just take all this right here, right there. Okay, so we had, let's get to our answer. We had, from here, we had 1/2 x squared plus x plus, now we're going to do a new integral, right? And I've already forgot my answers. What were they?
-1, 1, and 2.
-1, 1, 2. Okay, so A was -1, B was 1, and C was 2. By the way, the short method, you could have still gotten it. Okay, I just wanted to show you again the long method. All right, so we have A, which is -1. I'm going to put -1 out in front of 1 over x plus 1. So I'm grabbing these things right here, right? That's what I'm doing. Then I have plus B, so plus, well, a 1, I just leave it. So it's just 1 over x minus 1. And then the last one is plus 2 times 1 over x minus 1 squared. All of that dx. Any questions? We should be able to handle these. Constant over linear, constant over linear, constant over
Repeating linear.
Repeated linear.
repeating linear. That was a little different, okay? The first two are going to be natural logs, but the last one is not. So we're getting close to a final answer here. Okay, I'm going to have this integral here, which is going to be minus natural log of x plus 1, no scaling necessary, plus this one here, that's, again, no scaling, natural log of x minus 1. And then let's see, this right here from last class, I told you all to think that kind of looks like an integral of u to the -2 du, right? It's kind of like, it's almost like a 1 over u squared, and that's going to be u to the -2, and then that's going to become -u to the -1 when we take the antiderivative. So we're going to have -2. That negative comes from the fact that I have a negative when I take the antiderivative. And then u, which is the x minus 1, and then to the -1, and then plus c. There it is. Bam! Knocked it out.
So I had a random question.
Yeah.
Can you go back to your first page?
Oh, yeah.
Okay. Yes, can you scroll down? So since you can find A and C using the short method,
Yeah.
could you find, the values there and then, either to continue on using the short method or plug those values into what you did on the bottom? Yeah.
Yeah, you could plug A and C in right there.
Okay.
Yep. Yep.
Just wondering.
Yeah, I mean, there's definitely a shorter way through this, but I want everyone to be comfortable with the short way and with the long way, because there are problems where the short way, you can't get any information. Like you can't get A, B, or C, and all you have is long division. I mean, sorry, the long way, the long method. Okay, we have 14 minutes. Let's see if we can at least start the next one. Yeah, let's do this one. How are y'all feeling?
Not bad
No?
yet.
These problems are, they're bringing a lot of things together, aren't they? I mean, things from the past. On top of that, we have to know how to do some integration, but a lot of this is algebra. A lot of it is. All right, here we go. I'm daydreaming. Okay, we're gonna go here. Do we need long division?
No.
No. Okay, so, and it is a rational function, so we don't use long division. So we need to factor the denominator, if possible. Does the denominator factor?
Can take an X out.
Yes.
Got it, right? You can just peel an X out.
Is there any property for x squared plus 2 square?
Nope. To factor, no. There is no formula to factor a sum of squares. We have difference of squares, but no, there's no formula for it. It's not that it doesn't, it's not that haven't found one, it just doesn't exist. Not over the real numbers. You can factor that over the imaginary numbers. You just can't factor it if you're only allowed to use real numbers. Right? Because I could do this. If I did x plus 2i times x minus 2i, then that would be x squared plus 4. Because you do x times x, that's x squared. You do this times this, that's negative 2i times x. Then you do this times this, that's positive 2i times x. Then when you do the last one, you get minus 4i squared. But I squared by definition is -1. So you put the -4 and the -1 together and you get plus 4. The middle terms cancel and you get x squared plus 4. So you can factor x squared plus 4, but only over imaginary numbers. Yes?
Okay.
We're not allowed to do that here. Are you ever allowed to? You might ask that question, right? Are we ever allowed to do that? Like mess with imaginary numbers? Yes. There's actually an entire sequence of courses called complex variables. And what you do in a class like this, you only usually take complex variables if you're a math major. What you do is you start out and you say, hey, guess what? Remember those imaginary numbers that we stayed away from? We get to mess with them now. And you basically go through and you talk about all the algebra and calculus that you can do with imaginary numbers. And that's where I focused all my research in grad school. My thesis and stuff was all in imaginary numbers. So I'm partial to that. I love that topic. Cal 1, Cal 2, Cal 3 at this level, we don't even touch imaginary numbers. Don't even touch them. And there's a reason why. Do you want to know why?
Wait.
Yeah, I'm off topic now. I'm already there. The bus has already left the station now. So look, let's just think about a real valued function. F of x equals x squared. Oh, let's go even easier. Nah, I'll go x squared. What the hell was that? Okay, so when you think about a function like this, you have an input and an output, right? And we actually have pictures that we do in like algebra classes, like domain and range. So if you take a number like 3, send it through this function, it comes spit out as 9, right? Take a number 4, goes through the function, gets squared, comes out 16. So we naturally say, is there a way to visualize this? Is there a way to visualize what this graph is doing? And what we say is, yeah, I mean, each of these things going in here is a number, right? The 3, the 4, those are numbers. So everything going in is something that comes from a number line. Yes? So this is coming from a number line. I'm going to call it, y'all seen that notation for the real numbers?
Mhm.
So what's in is a real number, and what comes out is also a real number. So what I can do is I can visualize the input on a number line. So here's my input. So like I could visualize, here's 0, here's one of my inputs. Here's 3, right? 3 is my input. Now my output, I can visualize that on a number line also. The output went to 9. So I could say that that 3 gets sent to this number 9, yes? But that sucks. Instead of doing that, we can take this and like turn it and put it vertically like this. And now when we say plug in 3, it spits out 9, we have this idea of this point. And then when we plug in 4, we have this 16. And then when we draw all that together, we get a parabola. So what we're doing when we graphic function is we're visualizing the input as something off a number line, and then we're putting the output as another number line. The reason why we don't do complex variables, I feel like I've told you all this. The reason we don't do complex variables is because if you take a function and you're allowed to plug in a complex number, we use z instead of x, then you need to talk about the input and the output. So the input is a complex number, and complex numbers are numbers like 3 plus I. You could have just I, you could have 5 is a complex number, just 5 by itself. Every number you've already known in your whole life is a complex number. 9 minus 2i, those are all complex numbers. You send them through a function and they become something else over here, but they become complex numbers. So you're going from a complex number, we use a scripted C for complex, and it's spitting out a complex number. So let's say I want to visualize this. Well, to visualize this, in order for me to show you a complex number, I actually have to give you, it requires 2 dimensions of space. Because like for 3 plus I have to go to the right 3 and up 1. That dot in 2-dimensional space represents that number 3 plus I. And then I have the output, which is going to be some complex number over here. So that thing gets sent somewhere over here. So what if I'm trying to put these two together? What's wrong with me trying to put these 2 things together into a final graph? I know I've lost somebody, it's okay. So
No,
back
they're
here-
not on the same spot. They're not on the same area, quadrant or whatever.
Look,
No.
this right here, back to this original problem. For the input, we needed a real number line, right? That's 1 dimension of space. For the output, we need a real number line. That's a 2nd dimension of space. We can visualize 2 dimensions of space without problems. Here, complex numbers requires 2 dimensions for the input and 2 dimensions for the output, which means if you ever want to put them together, you're going to need 4 dimensions of space.
Oh,
Good luck, right? So what happens is as soon as you bring complex numbers in, you're dealing in 4-dimensional space. And that's why you don't see complex numbers till after you've done a lot of math, because you have to be like at a mathematical maturity level that you can start thinking about functions that you're not ever going to be able to see. Does that make sense? So it's much more complicated, but it turns out to be a very beautiful subject because basically everything that you do in complex numbers, you can translate into real numbers. So you can take a
So
number.
that's why you were able to see that unknown 0.
Well, that's different. That's still pretty advanced, but complex numbers, complex variables is just it's a different world, man. It's eye-opening. Okay, so I was distracted by myself here. I've lost the problem. Where the hell did I put it? Oh, there it is. Okay, so this, we're not gonna have enough time. We have 5 minutes, but I want to at least set it up. Don't have to do, we don't have to do long division, but we factored, and all that came from the fact that x squared plus 4 can't factor. All right. So here's where we are. Can't do anything else. No more factoring. So let's talk about the factors. What is this first one?
linear.
Linear. Okay. What about the second one?
Quadratic?
It's an irreducible quadratic, irreducible quadratic. Okay, so we have one linear factor, we have one irreducible quadratic. So what I'm gonna do is I'm gonna do partial fractions on this. And you know how we were doing just a second ago, like A over, the linear factor, B over the linear factor, and we're gonna do the same thing with one little change. The linear factor we have is still gonna give me an A over X here. Nothing changes with that one. That one's just what it's been, okay? But if you ever have an irreducible quadratic, you don't put B over that. You don't. What you do is you put
Bx plus c?
Bx plus c over that. So think of it this way. When you had a linear factor, right? When you have a linear factor, what did you put on top of it?
A.
A constant, right? That's 1 degree less than what you started with. You started with linear, which is degree 1. On top of it, you put just a constant, which is degree 0. If you have an irreducible quadratic, then what you're going to put on top of it is 1 degree less, which is linear. Now, if we can figure out A, B, and C, if we could at this point, then would you agree we have a constant over a linear, which we can integrate? And the second one would be a linear over a quadratic, which we should be able to do. We did that last class. That was the one where I said, I do it a different way. If you go see a tutor, okay, that's what this is going to become.
So, and the
Oh.
reason why we added the other constant was because of the 4?
No, it's because it's an irreducible quadratic.
Okay.
So every time you have a linear factor, you put just a letter on top, right?
Yes.
Okay. Every time you have an irreducible quadratic, you put a linear expression on top of it.
Okay.
Okay. Now, I'm going to offer this as if you finish on your own. Let's make it a quiz. Let's make it a quiz. My other class already has 2 quizzes. So let's make this a quiz. I don't mind if you work together on this, but just, what you need to do here is figure out what A, B, and C are, right? So clear your fractions, figure out what A, B, and C are, either the short method or long method. And then once you find A, B, and C, you've got to go integrate those. And the first one will be easy, but the second one's going to be some work. I'm curious to see how you do. Yeah. Homework wise, you can start the homework for sure. Let me just see how far you can go. Okay, in theory, you can get through the first 20 problems. All of those break down to be either linear factors on the bottom, or they turn out to be repeated linear factors, which we just did in an example before this. After 20, you start to get these irreducible quadratics, which I really haven't shown you an example of. This quiz is more just to see like how you do with it. Without me showing you how to do it, I just want to see how you do with it. All right.
When's it due?
Yeah, so when is this due? Let's make it due before class next time. So I'll send a Dropbox link right now, and then you can just drop it in there before class, and then we'll just see how the class does. Did y'all notice I updated the grades?
Yeah.
Update the grades? Okay. So the grades are there, and I think I even sent you back your quiz with any markups on it. So I think you go through Canvas, click on the grade, actually click on the grade of the assignment, and I think it brings up a little dialogue for you to see what I said or what I sent you.
Do you think I will be able to do this quiz and the homework problems without the TI-84 calculator?
I think you'll be able to do the homework and this quick, well, you know what, this problem right here. I don't remember where I got this problem, if I made it up or if it came from the book. You know what I would advise you do, since you're at home and you have access to a computer, I would say if you can't get a calculator, at least for now, for the homework, just go Google like system of equations solver. And I'm sure you'll find a website where you can type in the matrix and it'll solve it for you.
Okay.
Yeah,
Okay. I'll do-
I'm sure there's something out there.
Okay.
But before our test, you want to try and see if you can't get that squared away.
Okay. Otherwise, I'll just buy one.
Well, I don't want you to have to buy one. Do you not have a graphing calculator later yet?
No, I don't.
Okay, well, don't go buy one. They're not cheap, you know. Try and see if you know someone who has one that you can borrow or something, or go buy one. I don't know. Just,
Okay, I'll see.
yeah. What's your major?
Computer science.
Yeah, you probably need one at some point. I mean, I think at some point you're going to need a graphing calculator.
So
think
which one should I just get?
My opinion, if y'all need to go, you can go. If you have questions, I can hang out for a little bit longer. You know what? I mean, when it comes to calculators, graphing calculators, I have a few different kinds. I have the TI-84 Plus, which I think is more than sufficient for the things that you'll do. All right, I think that's TI-84 Plus. I also have a TI-89, which is this one right here. This is my baby right here. This is my baby. I love this calculator, and I only love it because it suffered with me. Like it was there with me in graduate school, and like we've been through shit together. Okay, so that's why I love this one. And then I also have the TI Nspire, and I personally hate this calculator, just personally, because it has a completely different interface than the interface that I learned. And for me, this is just it's trying to be too user-friendly. And my brain already works like this, which is very old school drop-down menus type stuff that I like this. But any of these would work. I just think you should go with the cheapest one, which I think is like the TI-84. I mean, does anyone else have an opinion? Does anyone else have an opinion as a calculator?
I have the Inspire, and it's not bad. It is kind of like complicated to use because it's like kind of more computerized. But you can probably go on OfferUp and find like used calculators, or maybe go to pawn shops to find used ones too. And
Yeah.
they're cheaper.
Exactly. Like the Nspire, I think it's not my generation. I think that's what I have to admit, is like the Nspire is more for a different generation that came up with more point click than I did. Because doesn't it have like a little mouse pad in the middle?
Yeah, it has like a little mouse pad. I just got lucky because one of my my pre-cal classes in high school like basically taught us how to use these things.
Yeah. So see that the TI-84 Plus is $110, man. That's freaking expensive. The TI-86, I don't even know if they make the 86 anymore. See, that's old school. I have that TI-86. How about the TI-89? Do they have that anymore? Oops, TI-8. 136. So look, I will say this. You have to be careful because the TI-89 has what's called a computer algebra system, which means it can factor, it can do differentiation, it can do integration. And a lot of times those tests or those calculators are not allowed on certain tests. Like as you move on and do more math and do more classes, they may say you can't have a computer algebra system on your calculator. So I would avoid the TI-89 if you're worried about testing later. That's just my opinion. Like standardized tests most likely will not allow you to use the 89.
Yeah, I understand, because right now, since it's like Zoom and all that, so there's no chance of looking, but like in in-person classes, I'm pretty sure.
Yeah. Trying to see if, so Amazon has 84 plus $75. Yeah, but you should invest in one. I think it's worth. Oh, you know
Yeah.
what? Hey, you know what? I just thought about this. Did you see what I had on the screen a second ago? I'm
No.
using Emulate. Now, this would just be a temporary fix. It wouldn't be a permanent fix.
Oh, the calculator you were using?
Yeah, so that I did all that for free. I didn't pay for any of that. Let me see if I can bring up the screen. So I downloaded this thing called Wabbit Emu. Wabbit, like Wabbit. Wabbit Emu. Emu stands for emulator. I downloaded that. And if you download that to your computer, you know what, I'll send you the link through the chat. I'll send you everything you need for it, actually. Wabbit Emu. Okay, so if you go to this website, you're going to download at this link. Okay, and let me send this in the chat. Okay, so you go to that link. Now, when you open that software, it's a little weird because every time you open it, watch, when you open the software, what it does is it brings up this window right here. And it says, which ROM do you want to use? And so I have to browse my computer to get the ROM that I want. So I'm having it bring up the TI-84 Plus. So I click that and click finish, and it drops the TI-84 Plus in my screen. Okay, so you also need the TI-84 Plus ROM, which I'm going to send you right now. Where the hell is it? It's on my desktop. Where is it? Yeah. So I keep the ROM that I'm going to use on my desktop, and then I have a shortcut to this program. And so every time I open it, I just open up that ROM, and you can. Does that make sense?
Yeah.
Okay. I mean, that's
can you
just,
send it
just
to
you wanna
me
know.
via Canvas?
Can you not get it here?
I did, but I'm on my
you're
iPad,
on
so
your phone.
it goes away.
Yeah, I got you. I think there's, well, yeah, never mind. I'll send it, but before I do anything else, if you go to, you can go TI ROMs, you can go to TI ROMs, and if you click on that, you can actually pick which emulator you want. Like if you want the TI-89 ROM, you can do that ROM also. So you can download that. It doesn't have a whole lot of them, but it has enough of them. So look, I can bring up the ROM I just downloaded. Now it should bring up the TI-89. Oh wait, that brought up the 83. You know, I think I clicked the wrong one. Did I click the wrong one? No, I did that one. It's weird. Maybe it's in the wrong place.
It's because in my even calculus class, my teacher would let my friends do differentiation with the calculator, but like I was more into doing it with my hand, so I never bought it.
What class?
It was calculus 1.
Really?
Yeah. Like my friends had TI-84 and 83 plus, and there was no, and I would use my Casio.
You can use a TI-84 to take the derivative of a function at a single point, but you cannot use a TI-84 to find the derivative of a function in general. In other words, if you're using a TI-84 and you want to know what the derivative of sine of x is, it won't tell you. But if you want to know the derivative of sine at the value 2, it will. Okay, I'm going outside of what I want to discuss here. So, okay, have I addressed everything here? Because I do have to run.
Yes, sir. Thank you so much.
All right.
Question
Yes.
about problem C.
About what?
About the previous problem that we just did, C. I just don't understand how we got
Here,
the
This one?
half x squared plus x.
Wait, is it this one?
Yeah,
Okay, so how we got what?
after we did the long division, or we got the second integral on the right, where is the half x squared plus x?
This right here?
On the left. Yeah,
Where did that come from? So when we did the long division, we had an x plus 1 plus all this junk, right? Okay, so I put that into my new integral, and then I actually found the antiderivative of x and found the antiderivative of 1.
okay, thank you.
You sure?
Yeah, I just, I didn't write that previous part down.
Okay, yeah, so that comes from here. And then this part we didn't know, so we had to kind of work that out still, and that's where all this came from.
Okay, I got it, thank you.
Okay. Any others?
So when we have our exam, we're allowed to use our matrix calculators on our, yeah, okay.
Yeah, I'll let you use your calculators for sure. I really don't want to have you use a computer, but like for certain students, if they can't get a calculator, then what I'll do is I'll say, okay, if during the test you need to solve a system of equations, then you need to like send me a chat, say, hey, I need to go to my computer for this one thing, and then they go solve it and come back and that's all they do. Maybe I'll do that, you know, but otherwise, yeah, you'll just have to use your calculator.
Okay, no, I was just wondering. Because I remember when we recal and he didn't let us use calculators at all.
Yeah. No, because I mean, this, if I had you solve that a system by hand, I mean, that could add 30 minutes to the problem. You know, I mean, it could. Doing elimination could add 20 minutes, 30 minutes to a problem. And I'd rather you show me that you know what you're doing in terms of the calculus than to go back and rehash all the algebra. I think there's enough algebra here that we don't need to go through elimination again.
Well, I need to go cut down a tree, so you have a good day.
All right. Sydney, you have a question or are you good?
No, I'm good. I was just working on the problem and forgot to leave. Yeah, good day.
Okay, take care.